This paper is on resource-aware cost-sharing mechanisms with priors, and it is joint work with Emmanouil, Pountourakis, and Alkmini, Sgouritsa. And in this paper, we focus on scheduling games, where we have a set of machines. Each machine has a cost function that characterizes it. And these agents are strategic. Their goal is to try to choose where to schedule their job. Each one has a job. They're trying to schedule it on one of these machines. And once they do choose a machine, this induces a cost on that machine that depends on this cost function. But of course, their incentive is to minimize their own cost, which is determined by a cost-sharing mechanism. So for instance, the most natural choice would be equal sharing, to share the cost of the machine equally among the users. So in this case, for instance, if all 6 users choose the left machine, the cost that it induces is 6. If you share it equally, each one of them pays 1. So if you observe this and see the other cost function over here, the other machine actually would be much, if we moved all the jobs to the other machine, they would only pay a cost of 2. So that would be a much better outcome in terms of the social cost. However, this current assignment is a Nash equilibrium. If you observe that if any one of these agents were to unilaterally deviate to move to the second machine, they would be the only one there. The cost they would induce would be 2, and they would have to suffer the whole thing on their own, and therefore they would rather not deviate. So this is a classic example where this equal sharing, cost-sharing mechanism will lead to very bad equilibria. It can be really bad because we can scale this to be linear in the number of agents. So the question that we ask here is, how can we change this sharing? How can we make it more informed to try to actually do better than that, to avoid these issues? So formally, each machine J has a non-decreasing cost function, Cj of L. L is the load, the number of jobs assigned to that machine. And we denote it as Lj of S. So once everybody has chosen a machine, S is the schedule, we get an Lj of S as the load on that machine. So our goal is to minimize the social cost. So in other words, the sum of the costs of all the players, given the choice that they made. So a cost-sharing method, Xi, defines this share. So this is the handle that we're going to have in the problem. We're going to be determining the cost-sharing method, which determines the cost of the users, and therefore really changes their incentives and the equilibria of the induced game. And given a class of games G, where F and a game within this class, I mean, everybody, I guess, knows the definition of the price of anarchy by now, but for completeness, if F of G is the feasible schedules and E of G is the pure Nash equilibria of this game, the price of anarchy is the supremum over all games in the class of the worst social cost one could get in equilibrium over the optimum they could get over all feasible outcomes. So our goal, therefore, is to try to make sure that even in a decentralized way, we get a good outcome in this load balancing setting. Okay, so the cost-sharing mechanisms that we're going to be focusing are resource-aware cost-sharing mechanisms, which need to be decentralized. They cannot know everything about the system. So in fact, these resource-aware cost-sharing mechanisms can observe what other resources are in the system and their cost functions, but they cannot be aware, they're not aware of any players that are participating other than the ones that decided to choose that machine. And the whole difficulty here is how to design a resource-aware mechanism, despite this limitation, the fact that we cannot see, each machine cannot see what other users are in the system, and nevertheless achieve a good price of anarchy with this limited, decentralized approach. So the main question of this paper is, can we design resource-aware cost-sharing mechanisms that achieve a low price of anarchy for general families of cost functions? And prior results have achieved this, have achieved some positive results, but they were all for special classes of instances. Either the cost functions were all convex, or they were all concave, or a mix of the two. And as I'm going to argue a bit later on, these are really convenient special cases. But beyond these special cases, these mechanisms face major obstacles. And the main result that we achieve is we saw that if we enhance resource-aware mechanisms with just a limited amount of information about these users, we don't need to know every user that's in the system, but if we know just a little bit of information, we actually achieve good price of anarchy bounds for a very general class of cost functions. In fact, any bounded cost function where all we require is that the jump, if we, the load increases by 1, the jump is just no more than constant. So that even captures exponential cost functions, polynomial cost functions, almost anything you could imagine here. And our results are that if the mechanism knows just the users, apart from the ones that are using that machine, if it just knows 2 users that are definitely in the system, we can, with just this information, we achieve a constant price of anarchy for any bounded cost function combination. And then we also consider the setting where we don't really know anyone in the system, but we have a probability for with which they are participating. And in that case, we achieve an expected price of anarchy that is logarithmic in the expected number of users. Okay, so in the rest of the talk, I'm going to try to convince you, I cannot go into details. I'll try to convince you at a high level what are the obstacles are, how we manage to overcome them, and what the cost sharing mechanism looks like, but I have to really sweep several details under the rug. So I'll start with the structure of the optimal solution. And just to argue how much more complicated it is to go beyond convex or concave cost functions. So the thing is, if all the machines, here we see the machines at the bottom left, and we see the optimal social cost as a function of the number of agents in the right, if all these machines have cost functions that are convex, then actually computing the optimal solution is trivial with just a simple greedy algorithm. If we have one job, we look at the smallest marginal cost, and that's where we assign it. If we have two jobs, we just add the second one, looking at what the next smallest marginal cost would be, the third one, the fourth one. We just gradually can build the solution, and without throwing away, without changing any of the jobs we already scheduled. And this is really important because this is what allows us to actually get a low price of anarchy in a decentralized setting, that this optimal solution, which we're trying to achieve in a decentralized way, is actually very structured. Similarly, if all the cost functions are concave, first of all, also the optimal social cost is going to be concave. But the thing to observe now, it's a little bit trickier. It's not as simple as convex cost functions. The structure of the optimal solution, though, is still very useful. What we know now, if all the cost functions are concave, we know that the solution that minimizes the social cost is always going to assign all the jobs on the same machine. Because if it's concave, once you've essentially paid the initial cost, then the more jobs you add to the same machine, the better the marginal cost. So it could be that the solution with one machine, the optimal solution with one job is this one. It might move around with 2, 3, 4, maybe it stays at the same point. But you see that no matter what the number of jobs, the optimal solution always assigns them to the same machine. And this is exactly the structure that was used to achieve a constant price of anarchy for concave cost functions. Because although this is hard, to know which machine you should be assigning the jobs to, you should know what the total number of jobs in the system is. And you don't know that. The resource-aware cost-sharing mechanism doesn't have this information. But nevertheless, knowing that this is the structure that the optimal solution satisfies helps achieve a resource-aware mechanism that gives you the optimal solution in equilibrium. So these were the easy cases. This is why previous results actually managed to work. However, the moment you go beyond convex and concave cost functions, we see here that we get an optimal cost function as a function of the number of agents that is more complicated. The optimal solution can just vary quite a lot. Depending on the number of people that are participating, the optimal solution can change, the structure can change dramatically from round to round. So for instance, it could be that the first 3 jobs, if you have an optimal solution, should go in the same machine, but then if you get 4, it should be different. Later on, should be spread out across multiple machines and change as well as you go on. So this means that there's no useful structure if we deal with instances where the cost functions are general, they're not necessarily either convex or concave. There's not much to understand about, there's not much to tell about the structure of the optimal solution. So how can we, in a decentralized way with cost sharing mechanisms, manage to generalize these positive results in this classic problem? And this is where we go to the second part of our results, which is we achieve that using an online algorithm. So we provide an online algorithm. In simple words, instead of trying to implement the optimal solution in equilibrium, since this changes radically and it's moving around a lot, we instead define a surrogate. We define an online algorithm that is well behaved, and we instead try to approximate that algorithm, not the optimal solution. So let's what this online algorithm does. And of course, the whole point is that this online algorithm has a good competitive ratio. It is a good approximation of the optimal solution. So rather than going for the optimal, we're defining an alternative allocation that is well behaved and a close approximation. So let me define what this looks like. So given an instance with arbitrary cost functions, just monotone and bounded, bounded is actually we use it just for the for later on for the cost sharing. Here, this algorithm applies more generally. What we do is we look at the solution we look at all the points where the optimal cost becomes a power of 2, essentially. So we start off and look at, what if the optimal cost is 1? What is the largest solution I can get where the optimal cost is still no more than 1? And that optimal solution, in this case, you see there would be 3 jobs. It would look like this, and we mark it using our first color. These are this optimal solution, if opt is 1, would use these 3 jobs. These 3 slots, rather. Now we double that and consider what would happen. What's the largest solution where the optimal cost is still less or equal to 2? And as I said before, this can be quite different. Maybe all the jobs now are assigned here. We see that there's 5 jobs in that specific solution, and it could be quite different than the previous one, but we just use a different color and we mark all the new slots that we used for this solution. And as you can imagine, now we go to 4. We look at what is the point at which, again, the largest number of agents for which opt is still less or equal to 4. And we get this solution where you see now it's using some of the previous slots, but we use a third color only to mark everything that's used, all the new slots. And so on. We move on to 8. We do the same thing. Maybe the solution looks like this. We use a fourth color. We color all these new slots. Go to 16. So we use this doubling trick. Look at that solution. Again, it might be using a bunch of slots that have already been marked. We only use the color, the fifth color, to mark all the new slots. So long story short, at the end of this process, and this we can do in pre-processing time. This is not the online part of the algorithm. We just know what the cost functions look like, so we can do all this in pre-processing time. What we do then is we order all the possible slots based on the time at which they were visited. So we get this ordering. We get 1, 2, 3 because these slots were the first ones visited, and then 4, 5, 6, 7, 8. These were the next ones. Then we go 9 and so on. And essentially, the online algorithm does the following. As the jobs arrive, it doesn't know how many jobs will be present in the system, but as they arrive, it assigns them according to the ordering of the slots. So it will assign the first one here, second one here, third one here, then 4, 5, 6, 7, 8, then it will go to 9. And it doesn't know when it will stop, how many jobs will actually arrive. But as we prove, and it's not that surprising in hindsight, it actually achieves a competitive ratio of less than 4. So it actually always approximates the optimal solution within a factor of 4, right? So this means that as long as our algorithm, the output of our mechanism is making sure that we're satisfying that same ordering, we're always going to get a price of anarchy of 4. So what is nice about it? I suggest that this is well behaved. The nice property of this is that we know this ordering in advance. We can predetermine, just looking at the cost functions of the machines, we can predetermine this ordering. And this is much smoother than the optimal solution. We know that it grows in a specific way. We don't need to move a job once we've already assigned it. And the main idea of our paper is now, having established this much more well-behaved alternative outcome, to try to implement that using a cost-sharing mechanism. Which brings me to the third part of our contributions, which is the cost-sharing mechanism itself. So even though I suggested we have now this ordering, as long as the tasks are assigned in this order, we'll be in good shape. We'll have a 4 approximation. How can we design a cost-sharing mechanism that ensures the only equilibria are going to have exactly this form, are going to be the outcomes of the online algorithm? And what we need to do is to ensure that if slot J is never used unless all the slots before it have been used, right? So if we use, for instance, slot 15, it better be the case that there's jobs using all the other slots leading up to this, 1 to 14. Otherwise, this would not be the outcome that the online algorithm would suggest. But how do we do that? How can we design a cost-sharing mechanism that achieves this? And the way we do so is the following. Let's assume that this happens. So you see now in red, a possible assignment where there's 1, 2, 3, there's jobs. The busy slots are 1, 2, 3, 4, 5, 6. There's jobs assigned to these. But the seventh one went to 10 instead of going to 7. How can we ensure that this will never be an equilibrium? Well, the way we do it, the main idea, and I'm going to stick to high level. Hopefully, if you're interested, you're going to come to a poster session or read the paper or reach out to us. But the main idea is the following. we assign special roles to a subset of agents. We call them the enforcers. And we give them the incentive to use the machine with the largest busy slot number. In this case, the largest slot that is being used is 10. That's the largest number. So these enforcers are actually going to be rewarded by the cost-sharing mechanism if they go and use this machine, right? So whenever someone's using a big number, the enforcer will try to go to that same machine as well. However, the agent using the largest slot in a machine with an enforcer is penalized. So in other words, if the enforcer goes there, then all the regular agents that are on the same machine, all the non-enforcers, are going to be penalized so that their cost is so much larger that they would prefer, if there's any slot, if 7, 8, or 9 is still available, the cost that they suffer if they stay in that larger slot because of the enforcer is going to be larger, and therefore they're incentivized to move to a smaller idle slot if one is available. And I know this is very high level. This is as detailed as I could get with this, but this is the main idea. And using these enforcers in a totally decentralized way, we can actually enforce that people are going to follow the order. Nobody's going to try to jump to a subsequent slot in equilibrium, that every equilibrium will be of this form. So what we have here then is the main results. So we have the results are of two flavors. If we have two users that we know are going to be present, then we just assign them the role of the enforcers. We just say these two users that we know are going to be present are going to play the role of the enforcers. And the only equilibrium is the outcome of the online algorithm. The only additional cost that we pay beyond the online algorithms for approximation is because we overcharge some people to ensure that this is an equilibrium. But we make sure that the outcome is has price of anarchy constant. And importantly, I didn't emphasize that yet, but it always possesses a pure Nash equilibrium. Our cost-sharing mechanism, and that's a non-trivial task to achieve. That took a lot of work to make sure, and a lot of special cases to address, to ensure that this mechanism always possesses a pure Nash equilibrium, no matter what the game is. And secondly, if we have a stochastic setting where each user is drawn from with a probability P, then an n tilde is the expected number of users, then actually we don't know exactly who is going to be there to choose them as enforcers, but we actually choose a roughly logarithmic in n tilde number of enforcers. And in expectation, that gives us a logarithmic price of anarchy. I'll just leave the open questions here, which are about extending beyond bounded functions, getting a constant price of anarchy, even with stochastic arrivals, and extending these ideas to more general networks. And I will thank you.